Hi, linear algebra students. Inverse of a matrix. Last video, third, to prove this very important theorem. So let's restate it. It's good practice. If an elementary row operation is performed on a matrix A of dimension m times n, the resulting matrix can be written as a product of an elementary matrix times A, where that elementary matrix has been obtained from I, from the identity matrix of dimension m times n, by doing the same elementary row operation. Okay, I won't remind you why this theorem is so important, but I will remind you that the proof relies on this identity. The fact that when you multiply two matrices together, you can find the ith row of the product by looking just at the ith row of A, how it multiplies with the entire matrix B. Okay, so now we're doing the row replacement. So row I becomes row I plus k row j. And as usual, what we're going to do is we're going to consider the elementary matrix that we get by performing the same row operation on IM. And we're going to prove that the rows of EA are actually the rows of the matrix that we get after performing this row operation on the matrix A. So that's how the proof is structured. Now I have a lot of letters. Look, I, K, J. So the index I will use now is L, let's say, right? So here I will just specify that K and J, I and J, K is actually the scaling factor, that the factor that we use to scale the row J, so I don't need to include it in here. Well, I and J are both between I and M, but they are not the same. So let's actually write this. Okay. Now, let's go ahead. Case number one. We're going to consider a row that is basically just not the row I. So a row that hasn't been involved in the row replacement. So row L, where L is not equal to I. So we would like to compute the Lth row of E times A. So again, as the same as before, right? We use this identity all the time. We use this identity. So that's the row L of E multiplied by A. And the important argument here is that this row hasn't been replaced at all. So it's the same row as the row of the identity matrix. So that's it. Since L is not equal to I, the row L of I didn't change. Okay. So this means that we're dealing with also the row L of the identity matrix. So then we regroup, and I times A is equal to A, so we get the row L of A. Okay, I'm going to erase everything, but what's important to note here is the difference between the Lth row of EA and the Lth row of A. They're equal, there's no difference. That's what's important to get. Okay, now I'm erasing the theorem and we will do the second case. So the case number 2, obviously, we're considering the row I itself. So now we have that row I of EA. And again, as usual, this part never changes. Okay, now tricky part, okay? Look at this carefully. This is actually going to be, in brackets, the row I of I plus K times the row J of I multiplied by A. Okay, so this is the important part right here. And to explain that, so I'll actually go ahead and write down the explanation. Okay. So remember that the row I of the identity matrix is something that looks like this. So we're going to have like 0 up to 0, 1, 0, up to like 0, 0, 0, and something like this. And you'll see where I'm coming with this. So this is the ith row, is the ith, right? So actually this is the ith column. That's it. And here I'm going to label the jth column. Okay. And then if I write the row j of I, okay, so that's what it's going to be. Where again, like this is the ith column, and this is the jth column. So what happens if we compute this? So row I of I plus k times row j of I. So what we're going to do is we're going to add these two things together. Okay? So I'm going to do it vertically so that you can see very clearly. So we have this. Plus k multiplied by this. Now keep in mind, what's going to happen here is that the k will multiply all of the entries, but they're all 0 except for that one entry. So that entry is going to get multiplied by k. So as we combine the result, we're going to have this. Okay. Now I remind you, this is the ith column, and this is the jth column. And as you can see, this is the result that we're looking for, that we obtain from I by the row replacement. So, which is the ith row after performing row I go to row I plus k row j on the identity matrix. Okay, so you need to be convinced of that in order for us to move on. Okay, so this explanation is exactly why we can replace the row I of E by this. Okay? Now I'm going to erase that explanation and I'm going to end the proof. So now that we have this, the idea is that these are matrices, okay? And matrix multiplication is, we call this, if I'm not mistaken, right distributive. There you go. So it means that this is the same as writing the row I of I times A plus K times the row J of I times A, right? We distribute on the right. Okay, and then we use the same identity on each term. Okay, so in other words, this is the row I of A plus K times the row J of A. Okay, and now we're ready to conclude. Here we go. So if L is not equal to I, we have that the row L of EA is equal to row L of A. And if L is equal to I, okay, actually, yeah, this is row L for L not equal to I, and this will be for row I. For row I, we have that row I of EA is equal to what we have over here. So row I of A plus K row J of A. And now we can easily conclude, look, EA and A have exactly the same rows, except for the row I, on which you do the row replacement, row I plus K row J. So here we go. So EA is obtained from A by the ERO, row I plus K times row J. And again, this is the end of the proof for that particular ERO. There you go. This is the end. We proved them all. This was the last video. Now I want to remind you, if you found this confusing, I want to remind you the good news that this is optional, right? You don't have to memorize the proof, and you won't have any assignment that will be based on this proof. But I just find it really cool because this theorem is exactly what allows us to prove that if a matrix row reduces to I, then it's invertible. All right, see you in the next video.